Magnetic fields are similar to gravitational fields in that both fields have the potential to exert a force on an object. When we're talking about gravitational fields, we draw our field lines starting outside the Earth and pointing in towards a circle. And gravitational fields exert a force on objects in the same direction that we draw our field lines. And that's where magnetic fields start to become very different from gravitational fields. Whereas a gravitational field centers around the center of mass or the middle of the object, magnetic fields center around the north and the south poles. And the field lines will do their best to travel from the north to the south pole. Instead of exerting a force in the same direction as the field lines, magnetic fields actually exert a force perpendicular to the field lines. So in this case, as this charged particle moves towards the field lines, it will actually slow down and then repel in a direction perpendicular to the field lines. The equation for the force that a charged particle experiences in a magnetic field is the force is equal to the charge of the particle times the velocity of the particle times the strength of the magnetic field times the sine of the angle. Remember that the sine of 90 degrees is equal to 1. The sine of any other angle is going to be less than 1. So the force from a magnetic field is the strongest when the charged particle is moving at a 90-degree angle relative to the field lines. So when we're talking about charged particles in a magnetic field, we're usually concerned about three things: the force exerted on the charged particle, the velocity of the charged particle, and the direction and strength of the field lines, which we usually describe as B in a formula. When we're talking about force and velocity and field lines, you simply need to remember that everything is going to act perpendicular to everything. To help us visualize that, we create the right-hand rule. The right-hand rule is a simple way to illustrate a three-dimensional world, where everything is perpendicular to everything. In the right-hand rule, your thumb indicates the velocity of the charged particle. Perpendicular to the velocity are the field lines of the magnetic field. And perpendicular to both the field lines and the velocity is the force of the magnetic field, which is shown by the direction your palm is facing. Because of the difficulty of explaining a three-dimensional process on paper, we create symbols to help illustrate the three-dimensional world. The symbol X marks a field line or a force going into the page. You can remember that by the old pirate saying that X marks the spot. If you see an X, you dig into the X. Out of the page is symbolized by a circle, and to me it looks a little bit like a bullet coming straight towards my face. So you might see a drawing like this, where you're asked to figure out the direction of the force exerted on the charged particle by the magnetic field. The velocity of the charged particle, that's going up. So your thumb should be directed towards the ceiling. Your field lines, those are going into the page. So your fingers should be pointing towards the page, or right now, towards your monitor. Your hand position should look like you're getting ready for a handshake. Your thumb is pointed upwards and your fingers are into the page, resulting in your palm facing to your left. And that is the direction of our force. So an interesting thing happens when a charged particle is put in a magnetic field. Initially, the charged particle experiences a force perpendicular to its velocity. In this case, that would be down. But the charged particle already has, in this case, a horizontal velocity, so it doesn't immediately go straight down. Instead, it begins to arc down. Once the velocity of the charged particle is changed, the force the particle experiences will also change. That means now the magnetic field is pushing the charged particle to the left. And that process continues until a charged particle begins to move in a full and complete circle. When you have a wire carrying an electric current through a magnetic field, the magnetic field lines begin to rotate. To illustrate this, we use another version of the right-hand rule. But instead of the magnetic field being in a constant direction, the magnetic field actually wraps around and turns around the wire. But in this case, the thumb ends up indicating the force of the magnetic field. Notice that by drawing the force up from the magnetic field lines, you always get a right angle. So the rule that the force is perpendicular to the field lines still holds true. So to sum up, there are two versions of the right-hand rule that help illustrate the direction of a force exerted on a charged particle. In both cases, we still use the equation that the force is equal to the charge of the particle times the particle's velocity times the strength of the field. In a static magnetic field, your hand will be open and extended as if you were going to shake somebody's hand. Your thumb represents the velocity or the direction of the charged particle. Your fingers indicate the field line, and the force is the direction your palm is facing. When a magnetic field is created by a current going through a wire, your fingers still represent the direction of the field lines. However, the field lines continuously curl around the wire, and since the force is always perpendicular to the field lines, your thumb has to indicate the force. This question here is a bit of a trick question because it's asking us to figure out the force of a charged particle as it travels against the field lines. You might think the field lines are going to be pushing the charged particle to the right. But remember, the full equation is the force is equal to QVB times the sine of the angle. If the charged particle is moving parallel to the field lines, then the sine of the angle will actually be the sine of 0 degrees, which is 0. Or in other words, there is no force. And that's something we should have known because the strongest force is when the velocity is perpendicular or at a 90-degree angle to the magnetic field lines. This question is asking us to combine our knowledge of electric fields and magnetic fields. We know electric charges create a field going from the positive to the negative. And like gravitational fields, electric fields exert a force in the same direction as the field lines. So in this case, if we only have the charged particle and the electric field, the charged particle will curve towards the right. The question wants the charged particle to travel straight down. So we're going to need another force traveling to the left to cancel out the electric field. This one's a bit challenging, but we're still going to be using the right-hand rule. The velocity of the charged particle, that's going straight down. So your thumb should be pointing down towards your lap. We want our force to counteract the red electric field lines. So our palm needs to be facing towards the left. So see if you can figure out a way that your thumb is pointed down and the palm, again, of your right hand is facing towards the left. The only way that I can get this to happen is if I stick my elbow out and I point my fingers towards my chest. So my fingers are touching my chest. My elbow is actually swung out in front of me so my palm can be to the left and my thumb can be pointed down. If your fingers are pointing towards your chest or towards your face, that's the direction of the field lines. So our field lines are coming right straight towards us or directly out of the page.